Hello, my name is Ryland Wallen. I'm here to talk to you all about ultrafast optics. I'm going to begin this discussion with atoms. Atoms are these teeny tiny little things that make up everything, which I think is pretty cool because both you and me are made of these little atoms. But because they're so small, it's really hard to see them. And not only are they really small, they're really fast. If we want to see things that are really small and really fast, we have to figure out some method. Historically, the way we see things that are really fast is by having something else that's faster. A long time ago, back in the 1800s, there was a bet between Edward Muybridge and some other guys about how fast do horses gallop. And when they're galloping, do they have all the feet on the ground or not? Well, they had to figure out some way to measure this. And eventually, Mr. Muybridge came up with a camera that could take the pictures of the horse really quickly so you could see the horse and see that it had not all of its feet on the ground. So he won this bet because on this picture here, you can see in one of these frames, the horse has no feet on the ground. So this one right over here. Yeah. This one right here. You can see that there is no feet on the ground of the horse. You can kind of see these really fast things. So let's now compare some broader things. We're going to have these timescales and kind of understand the timescales better. So when I was talking about these atoms, I was saying they move really fast. So let's understand how fast really fast is the relative graphic. On this graphic, we have on the far left side the electron motion and the molecular motion, which occur in an attosecond and a femtosecond, times 10 to the minus 18 and minus 15. These are really, really tiny. So to put these in perspective, let's go to the other side of the graph. So here at the standard 1 second is something we can kind of comprehend. That's just like everyday life. We can feel a second. Well, if we go all the way over to the other side where it's the same distance away, a femtosecond difference, so times 10 to the 15, is the time since the Jurassic period. So all the way back to when the dinosaurs existed, which is like a really long time ago. Or if you go back to the speed of the electrons, all the way to the age of the Earth, the age of the universe. A really, really long time ago. So you can just tell these time scales are really fast. I was saying that these things are really fast, these things are really small, but what do we use to see them? We use light. Light consists on a spectrum, and the spectrum kind of has lots of different wavelengths and sets of different colors. And we can use these different colors to kind of see different parts of these really tiny things. And specifically the way we do this is using an ultrafast laser. And an ultrafast laser is a type of laser that has the laser pulses that are about the size of these in time. So an attosecond pulse is a pulse that lasts for 1 attosecond, which they said the same length of time as the scale of the age of the universe, but in the opposite direction. So much, very, very, very quickly. 1 billionth of 1 billionth of 1 second. And if we make these pulses really short, we can kind of flash with it and kind of see what's going on, kind of like a strobe light. Kind of give an example of what this is and do a little demo. I am going to do a little strobe light, and we will see this kind of principle in action. So if we could dim the lights. Yep. So you can see here, we have a pinwheel going, but you kind of see it in one spot with each flash. You don't see it very well because each flash is too slow to pick up all of the motion. So you get 1 instant of time with it. But if the pulsing of the light is really, really fast, something like this, you can see all the different steps of the pinwheel. You can see it kind of moving all around. So because of that, we can actually get, if we take enough of these pictures together, we can actually see how the pinwheel is moving. This is exactly what we're doing with our atoms. This method, when it's used to study atoms and molecules, is something called pump probe spectroscopy. And pump probe spectroscopy works by taking a laser that's pulsing really quick, kind of like this light here, and then sending it, so you have one beam of that light that's pulsing going in one direction, and going through this beam splitter, and then going through another one, and then coming and hitting our sample, and it's kind of hitting our sample at one spot, and it's making the sample kind of lit up and bright so you can see it. And then the second one comes through, and it goes through something called a delay stage, and it kind of makes it go back and forth. So the laser pulse light kind of goes through different sections of it, where you can see as that thing moves further and back, it changes where this light and this light interact. And you can kind of just use some math to figure out with the overlap what's happening inside. And if we know what's happening inside with each light pulse, each picture you're taking, you're able to recreate what's happening, and you can see exactly what's happening with the atoms. Here's an actual image of what the system kind of looks like. You have a sample, and here's a kind of real sample that people are currently studying. It is a little teeny crystal that is about the thickness of a human, or a little bit smaller than the thickness of a human hair, 10 microns by 10 microns. And we can just use a laser and hit that and kind of study it. And this is what the setup to study that crystal looks like. So while in the picture you saw, it looks very basic, and the detector looks like this little thing, in reality it's a very complicated system. And if you take the complicated system and take the data, this is kind of what it looks like afterwards. You get a graph, and the graph always kind of just goes up and comes back down. And all you're seeing when it does this is you're seeing the atoms change shape. So we have at early times when it's up really high, it means it's in one shape. It's kind of, in this case, a peanut-looking shape. And then as time goes on, it changes from being peanut-looking to a sphere, or to a ball. And this goes back and forth with time. Every time the one light hits it, it goes up, and then over time it goes back down. And you can kind of just see in this animation here, as the light hits it, it goes back and forth between going up and down and up and down. And this whole process of it going from peanut to ball kind of looks like this. And this all happens in about 1 to a few, hundreds of attoseconds. So really, really quickly. That is ultrafast optics in a nutshell. Thank you very much.